Okay, welcome to the third lecture on algorithmic meta theorems. Today we're gonna have the first highlight of the lecture. We're gonna introduce Courcelle theorem, and we're gonna start proving it a little bit already. Let's see how far we get with our proof. Just as a quick reminder, in the last lecture we introduced tree width. So, hey. So yeah, just a quick reminder, in the last lecture we introduced tree width, which is a decomposition of a graph into a tree-like structure. When we had our bags, we had these three properties that a tree decomposition was supposed to have. And we learned how to do dynamic programming with these tree decompositions. In particular, what we did is we rooted the decomposition and then defined our vertices Vi, which are going to be the ones inside the bags, and Vi, which are those which are somewhere in the bag below the current bag I that we're considering. And yeah, the way we did dynamic programming is by starting at the leaves with our dynamic programming tables and then growing those tables upward until we reach the root, where we can then read off the answer that we're interested in. Besides tree width, there was also introduced MSO logic. Sorry that it's cut off in the video. The top. Okay, so MSO logic, they could quantify over vertices and over sets of vertices. You could ask whether two vertices are adjacent, whether the vertex is contained in a set. And generally, you have some signature tau, which could be anything. So usually we considered the case where our signature tau contained the adjacency relation, which we denoted by tilde, and some set of colors, C1 for the first color, C2 for the second color. So these were unary relations. Today we'll also see why those colors are interesting and what you can do with them. And of course, you could existentially and universally quantify over these variables. And some more notation. So if we have a sentence and a graph, then we write this symbol here, G, and then the model's symbol, and then the formula, which means that the formula is true on the graph, or that the graph is a model for the formula. And with all these reminders in place, let's now get started. So this is now a little bit algorithmically in terms of model checking. So what is model checking? So the model checking problem is defined as follows. We have as input graph G and an MSO1 sentence phi. And the question that we're supposed to answer is whether the formula holds on the graph or not. So this is now the MSO1 model checking problem, because we're given an MSO1 sentence, but it could in principle be any logic. So for every logic, you can define the model checking problem. And first thing we can wonder about is what is the complexity of this problem? Of course, it is quite hard because MSO is a very expressible language, and you can show that in general, the problem is p-space complete. So the model checking problem for MSO1 logic, p-space complete. So p-space, the complexity class, is even larger than NP. So it's everything that you can evaluate with polynomial space and without any bound on the computational time that you can take. And so this is, so it contains the whole polynomial hierarchy, if I believe correctly. So it's a very powerful complexity class, so a very hard problem. So we have to take some structure of our graph into account, of course, which is going to be tree width. But first you can also wonder, like, can you parameterize the problem maybe by the length of the formula? Usually the formulas we're considering, they're short. So can you maybe get a running time of the form f of phi times poly n, or maybe only n to the f of phi? So this would be like an FPT or an XP algorithm in the formula length. But of course, this is also impossible because we saw that you can encode 3 coloring using the fixed formula of some fixed length. And then if you plug in this formula and you could evaluate it in time n to the f of phi, then you could evaluate the formula in some fixed polynomial time, and you had a polynomial time algorithm for coloring, which we do not expect to exist. So this means that if we parameterize by the formula length, then the problem is para-NP complete still. So if you don't know what para-NP complete means, it just means for every fixed parameter, for every fixed, there exists some formula for which the problem is NP complete. But yeah, so now we want to take our tree width of the graph as well into account. And this brings us now to the beautiful theorem that we call Courcelle theorem. And it states the following. So if we're given an MSO1 sentence phi and the graph, and we again want to decide whether the formula is true in the graph, then we can do it in this running time. And what is this running time? So we get a linear dependence in the size of the graph. So here this only depends linearly on the number of vertices in the graph. But we also have this formula, f of the tree width and the length of the formula. So if you had a parameterized complexity, it means the problem is fpt parameterized by the tree width of the graph plus the length of the formula that you're model checking. Or in other words, if your tree width is bounded by some constant and the formula you're evaluating is also bounded by some constant, then this formula, f of tree width and formula, this function also evaluates to some constant, and you get some real linear time algorithm for evaluating the formula. And if you want to phrase this a little bit more like a meta theorem, so far it's about evaluating formulas, but usually meta theorems are the form you can solve every problem of some kind. Then let's take some problem that you can express in MSO logic. And 1 second. Just trying to open the chat in case anybody writes something, so I see it later. Or you just speak up. Okay, so let's say we want to evaluate some fixed problem that can be expressed by an MSO formula of length k. Then this means that we can evaluate this formula in time some function of the tree width times k. But if we fix the problem, then the formula has constant length, so we can just think of k as the constant, and we get instead some function that depends only on the tree width for every fixed problem. So you can restate Courcelle theorem like this. Every graph problem that is expressible in MSO1 can be solved in time some function of the tree width of the graph times n, for where f is some arbitrary function. And we will soon see that this function f will be a very, very bad and fast growing function. But yeah, so far we're not going to worry about the proof yet. This will come at the end of the lecture and the next lecture, because it is quite a complicated proof, and we will rely on some black box theorems to prove this. But yeah, let's first think about what you can do with this kind of theorem. So we talked a lot about three coloring, and in the exercise we proved that you can solve three coloring in time some function of the tree width times n. And now we're going to reprove this with Courcelle theorem, and it's going to go exactly in the way that you would expect it to happen. So we know that three coloring can be expressed as an via some MSO1 sentence. So let's say we have sentence phi that expresses three coloring, and this means a graph is three colorable if and only if the formula phi holds. Formula phi looks something like this. And I guess it is the length of at most 100. So it has constant length, less than 100. And then Courcelle theorem states we can evaluate this formula in some function of the tree width and the length of the formula, which is less than 100. And so if you then say g of the tree width is f of the tree width and 100, then we get the statement here above that you can solve it in some function of the tree width times n. Okay, nice. So this is, of course, a much simpler way to get an algorithm if you only have to express it using the logic instead of designing all these ugly dynamic programming tables and making sure everything propagates correctly. For three coloring, it was easy, but if you consider more complicated problems, these dynamic programming tables can get quite messy. Okay, so this is Courcelle theorem, and this is our first application. If there's any questions up until now, please say so. Or still clear? My iPad is not working the way I hope it would. Okay. Okay, then let's come to the next problem. So let's next consider Hamilton cycle, and you can show that you can solve Hamilton cycle in a similar time, some function of the tree width times n, where f is some arbitrary function. And just a quick reminder, what is Hamilton cycle? You're given some vertices, graph, and some edges between them. And then you're supposed to find a circle that passes through every vertex. So you want to find a circle that contains everything. So maybe you start here, then here, then here, then here, then here, and here, and you would have Hamilton cycle. Okay. Okay, so we want to find an FPT algorithm for Hamilton cycle, and we have Courcelle theorem. And here's the bad news: Hamilton cycle cannot be expressed in MSO1 logic. But we still want to use our Courcelle theorem to solve the problem, but we cannot do it with MSO1 logic. So this is a bit of a tricky situation. So what we're going to do is we're going to consider an extended logic that we will call MSO2 logic. Some of you have maybe heard of it already. And then we're going to use the fact that subdividing the edges of a graph does not increase the tree width to reduce MSO2 model checking to MSO1 model checking, and then we can apply Courcelle theorem. So this is what MSO2 logic can do. So besides the usual quantification over vertices and sets of vertices, you can now also quantify over edges and sets of edges. So we call it MSO2 because you cannot quantify over one tuples, like single vertices, but you can also quantify over two tuples, like edges. And yeah, quantification of edges, vertices, sets of edges, and sets of vertices. And in order to make it clear that something is a vertex or an edge, we usually use letters like E or F for edges, and U or V for vertices, or uppercase letters for edge sets and vertex sets. And additionally, we have this incidence relationship, which tells us whether a vertex is incident to an edge. It is important that you can only quantify over edges. So you cannot quantify over non-edges. You cannot say there exists a set of edges that are not in the graph, only subsets of the edges that are actually there. Otherwise, the logic becomes way too powerful. We will maybe see this at the end of the next lecture. So let's see whether we can express Hamilton cycle. So the way I would express Hamilton cycle is by stating there exists a set of edges. So these edges will be the edges that form the cycle. And additionally, I want to enforce that these edges, they form some kind of cycle cover. So they should form a bunch of cycles that such that every vertex is in exactly one cycle. And on the other hand, we also want that the edges introduce a connected subgraph. And this rules out such a cycle cover, where you can cover it with multiple cycles. So the only cycle cover that is left is the cycle covers that covers everything with a single cycle, which is then a Hamilton circle. So let's start with the cycle cover attribute. So we have this set of edges. This is now the variable in our formula. We call it E, and we want to say that the set E induces a bunch of cycles that contains every vertex. In other words, if we have some vertex here, then there should be exactly two edges that are incident to this vertex. And this is enough to work exactly two edges that are contained in our set E. And this is enough to say that we have a cycle cover. So if we want to formalize this a bit further, we say for every vertex of the graph, there should be an edge E1 and an edge E2, such that these edges are different, and they should both be incident to the vertex that we picked. So now we have two edges that are incident to the vertex, and there should not be a third edge that is also incident to it. So there is no edge E3 that is different from the previous edges and also incident to V1. Then every vertex has exactly two neighbors in our edge set. And if you extend it like this, then this holds for everything. Then you have a bunch of circles like this. So I hope you see that this is a circle cover. And second property, connectedness. This is something we've done a couple of times already, so I don't want to go into too much detail here. We just say that every partition of the graph induced on this edge set E in two halves is such that there goes an edge from one part to the other part. So this is something we've seen a couple of times already. And I hope that you're now convinced that you can express Hamilton cycle using our MSO2 logic. On the other hand, you cannot express it in MSO1 logic, so that's interesting. And so with this logic MSO2, there is another extension of Courcelle's theorem, which states that basically you cannot only do MSO1 logic checking, but even MSO2 logic checking. So if you have an MSO2 sentence and some graph, then you can decide whether the formula is true, again, in some function of the tree width and the length of the formula times the linear factor in the size of the graph, the number of vertices. And this theorem I actually want to prove now because it follows as a simple corollary of Courcelle's theorem for MSO1. So what we're going to do is a very standard basic reduction trick that occurs a lot of times if you're working with these kind of logics. So we have some MSO sentence phi and a graph G, and we want to evaluate phi on G. That's what we have to do to solve this MSO2 model checking problem. And what we're going to do is we're going to construct some MSO1 sentence, phi prime, and we're also going to modify our graph a little bit. We're going to call it G prime then. So phi prime will be derived from phi, and G prime will be derived from G. And we want that first pair, the first formula is satisfied on the first graph if and only if the new formula is satisfied on the new graph. And is this enough to get a reduction? Or do we need some additional properties maybe? Yeah.
The length of the formula phi prime must be somewhat bound by the length of the formula phi.
Exactly. So we need that phi prime should be some function of phi. And why is that? Because here, if the size of phi prime can grow with n, then this function here, it will also depend on n, and we will have some horrible large running time. Do we need anything else in that? Yeah.
Tree width mustn't grow too large, depending on the tree of the original graph.
Exactly. The tree width should not grow. In fact, we will make sure that the tree width will be exactly the same as the original tree width. And one more property is what we need. So the last property is that we need that the number of vertices in the new graph will be linear in the number of vertices of the old graph. So if the number of vertices was quadratically suddenly, then our running time would be quadratic and not linear anymore. But we really want a linear running time in n here. So how do we do this reduction? So at first, let's construct G prime. So in our graph G, we can quantify over vertices and over edges, but in our graph G, question here, yeah.
Sorry, can you go back this way? It needs to be linear. It says n prime is in order of tree width times n. So how is that linear? How can the tree width not be? When the tree width of the graph, n is the number of vertices in the graph G, right? So tree width of the graph is in the worst case n-1.
Yes, so it will not be linear, but it will be a function of the tree width times the number of vertices. So we'll get another additional factor with the tree width, but this is okay. We can hide this additional multiplicative factor in our function f. Yeah, I was a bit imprecise there. Okay, so now we want to do the reduction. In G, we can quantify over vertices and edges, but in G prime, we're only allowed to quantify over vertices. So now this is no problem because we're going to modify the graph in the way that every edge gets turned into another vertex. So we're going to subdivide every edge and place a yellow vertex on this edge. So here, this edge here is replaced or is modified by having another vertex placed on this edge. And additionally, we're going to color the original vertices violet. So now the violet vertices correspond to vertices and the yellow vertices correspond to edges. And first, we're going to note that this modification does not increase the tree width because now we somehow have to incorporate our new vertices into the tree decomposition. So let's say we subdivide an edge UV by adding a vertex E, then we can create a new bag UVE that now contains all the neighbors of E. So we need to contain these two new edges that we inserted, and we just place it below the bag that contains UV. And this does not increase the tree width. And also the size of the new graph stays bounded because you can show that every graph with tree width W has at most O of W times N edges. So now we modified our graph. We also have to change our formula. And the important thing is now that we have to relativize our quantifiers. So whenever we existentially quantify over a vertex in the original graph, now vertices correspond to purple vertices. We say there exists a vertex which is violet and has this property. So before you would ask, there exists a vertex that satisfies phi. Now you ask, there exists a vertex that is violet that satisfies phi. So this way you relativize all the vertices there. And whenever you ask, there exists an edge that satisfies phi, you say there exists a yellow vertex that satisfies phi. So now we have make sure that we quantify over the right kind of vertices when in our formula. Of course, we do the same thing also for universal quantifiers. And the second important thing is that we also need to replace our atoms. So when in the original graph, we would ask whether two vertices are adjacent, like this guy and this guy, they would be adjacent. And in the new graph, we have to ask, is there a vertex E, which is adjacent to both of them? Or is there an edge vertex? So here we would quantify over this yellow vertex and ask whether it is adjacent to both of the endpoints. And this is true if and only if the vertices were adjacent in the original graph. On the other hand, if we ask whether a vertex U and an edge E are incident, this corresponds now to normal adjacency in our graph G prime. So we can just replace it with U adjacent to E. And I hope you see that G prime is a model of phi prime if and only if G is a model of phi after this modification. And this is something that this trick of slightly twisting the graph and slightly twisting the formula is something that occurs quite often, and we will use it later on in the lecture as well. Yeah.
Again, this thing about all WN edges, isn't it just this twice as many edges as before?
Twice as many edges.
in G?
Yeah, we don't need to bound the number of edges in G prime, we need to bound the number of vertices.
Okay.
But I guess the number of edges also is bounded because the tree width remains bounded.
Okay, but there's no direct connection between the tree width and the new number of vertices. So the additional vertices is just a number of edges that are there in the original graph. That's not related to the tree width.
No, I guess not.
So I don't get why they're connecting it to the tree width. So I don't get this point.
Why n primes remains bounded?
So I see that it's bounded, but not by. So this might also be true, but why do we need to talk about the boundary in terms of the tree width?
So let's say if it would not stay bounded, so suddenly our graph had a quadratic number of vertices. So would that be a problem in our?
So I mean, why are we expressing the bound in terms of the tree width and not in terms of the number of vertices and edges?
We're bounding the new number of vertices as a function of the old number of vertices.
Yeah,
So
that's fine. And the tree width.
yeah, but because we have to do that, because we cannot bound it just as a function of the old number of vertices.
Okay. And why is this true for new number of edges bounded by WN?
I'm not sure if I can give you a proof of that right now. So this is a fundamental property of tree width that a graph with bounded tree width has small number of edges.
I think have a tree position of only n nodes, and each node only contains W square edges.
Yeah, that's
only W squared in there, but you can also reduce it to just Wn. But there you get the bound of W squared times n, which will also provide us with just.
Okay.
Yeah, that's the right thing, exactly. So every bag can contain at most W squared edges, and
Exactly.
with some tricks you can also get it down to linear. So now we just proved that we not only can do MSO1 model checking, but we can even do MSO2 model checking on graphs of bounded tree width. And so now you can wonder, why do we even need MSO1? Like, isn't it much nicer to always work with MSO2? And if you're working with tree width, that's exactly the case. So tree width, it's always nicer to have W2 because it's more expressive. But the MSO1 result still has an important place in. Here's a question. How does the formula express that E1 needs to be in E? I'm not sure if
I think that's related back to.
Oh, I'm sorry. This was.
Sorry, I guess.
Many slides ago.
Sorry, I guess I'm a bit slow with checking the questions.
Yes, I didn't want to interrupt you, but now.
Okay, yeah, then let's continue here. So
Yes.
the nice thing is that you get this MSO2 result as a simple corollary. So for the actual proofs, you can focus on MSO1 only. But if you're working with dense graphs, then MSO2 is way too powerful. So let's say you have a dense graph, maybe some large clique. And here, if you have a very, very large clique, evaluating an MSO1 formula is trivial because you can complement the graph. Now it's just an empty graph. And whenever you ask whether two vertices are adjacent, you now ask whether two vertices are non-adjacent. So in the sense, you do the same kind of trick. You replace G and phi with G prime, phi prime, and then you evaluate that there. And this empty graph is bounded tree width, so it's very easy to evaluate it. So on cliques, MSO1 model checking is super easy. But MSO2 model checking suddenly becomes much more difficult. So if every edge is there, what you can say is there exists some set of edges E. What this really does is you can quantify over every possible subset of edges for a graph of size n. So in a sense, you can quantify over every graph of size n by just quantifying its edge set. So you could, if you take an arbitrary MSO formula, you could then express there exists some graph with n vertices which satisfies this formula by just quantifying over the edges of this hypothetical graph that would satisfy it using this existential edge quantification. And so this is a very hard problem, deciding whether a graph is satisfiable by some formula of length n, whether a formula is satisfiable by some graph of size n. And so this is something that you cannot do in FPT time, the way you can do it for MSO1. So next, so far we talked about yes/no problems, like is the graph 3-colorable? Does the graph have a Hamilton cycle? These are answers where you can just say yes or no. But oftentimes we also care a lot about optimization problems. So typical question would be, is there an independent set of size at least k? We know that you can solve this on graphs of bounded tree width because we saw the proof in the first, we did it manually using dynamic programming. Or is there a dominating set of size at most k? Is there vertex cover size at most k? And so what you can do easily is write a formula phi of x that is true if and only if x describes an independent set. So that is the easy part. But how do you express that this independent set has size at least k? You could do it as follows. You existentially quantify over k vertices. You say there is x1 to xk. They should all be contained in this independent set x, and they should all be different. So now you have a formula that says you have an independent set of size k. And what is the problem here? So, yeah.
The formula size depends on k.
Exactly. The problem is that the formula size depends on k. And so, but if you're looking for an independent set, the independent set can be very large. So maybe there's an independent set that has size roughly n, for example. If you want to check that using this trick, the formula would also have size roughly n, and that would be way too long. Our formulas can only have bounded size independent of the length of the graph. So if you're looking for a very large independent set that maybe contains half the vertices of the graph or something like that, then this becomes infeasible. You don't get this nice FPT running time. So we want a running time that is independent of the size of the independent set that we're looking for. And this is something that this following optimization theorem, this optimization variant of Courcelle theorem due to Courcelle, Markowski, and Ottix gives us. So this is a result about optimizing some MSO formula. So here again, let's break it down slowly. We're given some formula phi, and this formula phi is no longer a sentence, it has a free set variable. And also we're given the graph G as usual. And now we want to find some vertex set S star, should be some subset of the vertices of the graph. And this set S should be the optimal set that satisfies phi. So let's break it down as well. So first of all, the formula should hold after you plug in or set S star into the formula. And additionally, S star should be the largest possible set with this property, or the smallest, depending on what you're looking for. So let's say we're having a maximization problem, then the size of S star should be the maximal size among all sets that satisfy phi. or if you're looking for a minimization problem, should be the smallest set that satisfies phi. So in other words, if our formula phi expresses that X is an independent set, then what this theorem would give you a set S star that satisfies phi. So S star would also be an independent set. And what is this maximum number here? It is the maximum cardinality of a set that satisfies phi. In other words, it is the maximum cardinality of an independent set. So S star should have the same size as the maximum independent set. In other words, S star is a maximum independent set. Of course, this only works if your formula phi is actually satisfiable. So if you have a formula which has no solutions, then this theorem would give you some error message and tell you, okay, this formula is not satisfiable. But if it is satisfiable, you get an optimal solution to the formula that you're interested in. And this optimal can be in terms of maximization or minimization. So let's use this to solve independent set, just like as a recap of what we just talked about. So independent set, here with a graph G and an integer K, we want to find an independent set of size K. And this is the same thing as finding some set S star that maximizes this independent set formula. So we get the largest set, this maximal set S star that satisfies our independent set formula. And then we can check, is the size of this set larger than K? In other words, is the independent set larger than K? So this is the kind of approach that you use for optimization problems. Are there any questions about this statement or this approach? We're not going to prove the optimization theorem, but we're going to prove the basic version of Courcelle theorem, and maybe then I can give you a hint how you would generalize it to the optimization version. One more thing I wanted to express would be parity constraints. So let's say you have a property I want to express that graph G has an even number of vertices. I can't give you the proof, but it is also true that you cannot express this in neither MSO1 nor MSO2. So these kind of parity constraints, it's somehow impossible to express this using MSO. But there exists an extension of MSO that you may call CMSO, like counting MSO, I think is what it stands for. And there we introduced these counting modulo parity quantifiers. So we have this quantifier count or hashtag MK, and then we have this counts over some variable X. And what this means is that there are, so M is the base with which you're going to count modulo. So if M is 2, then you're going to count 1, 2, or 0, 1, 0, 1, 0, 1. So if you count modulo 2, then you just check whether something is even or odd. And then, so this quantifier expresses that modulo M, there are exactly K elements that satisfy phi. So if you have such a modulo counting quantifier, you can, for example, express that there's an even number of green vertices using this formula. So this states the number of vertices modulo 2 that are green is 0. In other words, there's an even number of them. You can even express some, like you can nest these kind of quantifiers and express that the graph has a Euler cycle. So when does a graph have a Euler cycle? It has one if there's an even number of even degree vertices, I believe, right? So you express that a vertex has even degree by saying the number of vertices modulo 2 that are y and y is adjacent to x is 0. So this is now phi of x. It expresses x as an even degree. And then you would next write the number of vertices number of vertices x that satisfy phi of x should also be 0. This way you would say an even number of vertices with even degree. So you can nest these counting quantifiers and you can mix them with the usual quantifiers. And this is CMSO1. And there's an extension of Courcelle theorem that you can even evaluate CMSO sentences in FPT time. The important thing is now that this number m, which is the largest base with which you count modulo, it also occurs in our functional dependence. So if you were to count modulo n, the size of the graph, so if you were to count exactly, then this would be very, very expensive and you cannot do that. So you can only count modulo some fixed constant or some parameter value. But this is a very nice theorem. You can do nice things with it. And something that you can also prove, similar to the base version that we're going to consider. And so far, I would like to summarize what we have so far already. So you have Courcelle theorem, and it can prove the basic version that we considered can prove MSO1 properties. And as a simple corollary, using the subdivision trick, you can also do MSO2 model checking. And if you are interested in parity constraints, even odd, then you can consider the logic CMSO, either CMSO1 or CMSO2. So you can mix these things. And you can also do optimization, finding a maximal set that satisfies some formula using the strangely named optimization logic variant LinMSol. So this is the name that they use in the paper. I find the name a bit strange, but this is what you should Google for if you're looking for the right reference. And this can actually do a lot more. So you can not just optimize the size of a set, you can also optimize some linear optimization functions. So if you have weights on these vertices and then optimize some linear combination of weights, this is also possible. And yeah, so we have a very rich family of variants of this Courcelle theorem. This version for LinMSol is basically the most general reference that you can find. And yep.
So that means that LinMSol can work with linear constraints?
Not linear constraints, linear optimization functions.
Okay. Yeah. Okay.
So you can, for example, optimize some set, and in this set, the number of red vertices minus the number of green vertices should be optimized.
Mm-hmm.
Okay. Any questions up until now? The other ones? If not, then I would like to dive straight into the proof. So this is a very nice proof, I believe. And historically, there have been different ways to prove Courcelle theorem. We're going to focus just on this base variant of MSO1. Model checking, no optimization, no edges, quantification, just the base version. And historically, this has been proven using so-called tree automata, where you were constructing some kind of automata that captured the different states that an MSO formula can be in. And then you traverse up the tree decomposition until you reach the root. I'm not so familiar with the details of this proof. And it's by far not my favorite variant of this proof. Today we're going to talk about my favorite variant, which is going to be using some deep logical theorem by Pfefferman and Ward as a black box. So this theorem, it tells you basically how you can combine MSO information about two subgraphs during a join step. And we're not going to prove a version of this. Maybe later on we're going to prove a version for first order logic of this Pfefferman-Ward theorem, but for now we're just going to use it as a black box and work our way around it. So The difficult part of the proof is going to lie in the join operation. So if we get the join operation running, then the rest, the introduce and the forget and everything, they're going to be easy. So let's focus mostly on the join operation here. So if we have a nice tree decomposition, we're going to assume that as well. We can get this nice tree decomposition all the time. Then the situation is as follows. We have our join back, which contains some vertices v1 to vk. And this join back has two children. These two children, they contain the same vertices, also v1 to vk. And each of those children has a subtree. And we're gonna refer to the vertices in the subtree on the left by f, and the subtree on the right, we're gonna refer to by h. And the way dynamic programming usually goes, you have some kind of solution in f, where the boundary is highlighted, and you have some other kind of solution within h, where also the boundary is highlighted. Then during the join step, you have to combine this into some kind of shared information on the graph f union h. So the picture I prefer for this is the following. So you have two graphs f and h, and they overlap somewhere, and the overlap are going to be exactly the vertices in our back. We call this overlap also the boundary. And we assume that the overlap of these two graphs, f and h, are exactly the vertices v1 to vk. And let's maybe see what we did for the independent set problem. So, or in general, usually we stored some kind of information in f, where the boundary is highlighted, and some information on h, where the boundary is also highlighted, and we want to then combine it into some form of information on the union of these two graphs, where again the boundary has some special purpose. And the way you would do it for independent set is you would store how all independent sets intersect the boundary, or slightly different, for every way that an independent set could intersect the boundary, you're going to store the size of the largest independent set. So let's say you have chosen these vertices in the boundary, the ones that are highlighted yellow. Then for the graph f, you would store, well, maybe I have the 5 highlighted vertices of the boundary, and additionally I have maybe 7 vertices that are hidden somewhere, and that is the size of the largest independent set in f. And additionally in h, you would again store, okay, I have these 5 in the boundary and maybe 9 hidden vertices somewhere, and that is the largest independent set that contains exactly these vertices from the boundary. Then in the join step, you can aggregate this in the way you would usually do. You keep the same 5 from the boundary, and you just sum up the counts for the hidden vertices. And yeah, we did this in great detail when we computed it the first time manually. And I hope this intuition here reminds you of what we did there. If there's any questions along this proof, just feel free to interrupt. So this proof is gonna build up and build up and build up. And if one step is not clear, then better make sure that you get the step early on. Yeah.
So we're trying to do the basic process here, which is for this decision problems.
Yes, I want to prove the basic decision version of Courcelle theorem. I want to show how to evaluate an MSO1 formula on a graph with bounded tree width and times some function of the tree width times length of the formula. Function of the tree width and the length of the formula.
And then there's one example of the independent set. What's the exact question? How is it formulated? Does there exist an independent set?
Yeah, so that's true. Right now, this was talking about an optimization problem, which we don't want to solve. Okay. Just like to get started with the idea of how it works again, I want to talk about what is familiar. So that's why now we're going to turn to a yes-no problem again. So let's say we have a yes-no problem of deciding whether a graph contains some subgraph with at most q vertices. So this is something you can express using FO logic even. quantify over all the Q vertices, and then they say that they should be adjacent in a way that they form a certain subgraph. So this is a special case that we have to solve. And here we can again build up some intuition. So far I want to mostly talk about like an intuitive approach and not yet formalize so many things. This will come in a moment. So let's say we want to want to determine whether the graph contains a certain subgraph. What we would store in our dynamic programming tables we would store how all subgraphs of size at most Q could intersect the boundary. So if the graph looks as it is highlighted here, then maybe in F he would store there exists such a subgraph, this spike, this path of length 2, and it contains V1 here and V2 here. This would be in our records for our graph F. And if there was another such path, then we would also store in our records that we have V2 and VK. So this would be two different records because it contains different vertices from the boundary. On the other hand, if we had a subgraph like this, then this would not lead to an additional record because these vertices outside the boundary, there we don't care which specific vertex we use. We can just keep them anonymously. It only matters whether there exists such a vertex that completes it to this path or it does not exist. So it's important that we distinguish the vertices in the boundary. The ones outside we cannot distinguish, or we don't need to distinguish. And for the other side, maybe we store as well that here we have some kind of path of lengths 1, 2, 3 that connects V1 and V2. And if we have this kind of information on the left side and on the right side, because the vertices are highlighted in this, the vertices from the boundary, we can combine it into the information. We can deduce that the whole graph contains this structure here, this kind of house shape bent over. And in case we were not distinguishing the vertices from the boundary, then maybe the graph where this spike was present, this one was not. If we were not distinguishing the vertices from the boundary, then we could not distinguish between this spike and the other one, and we could not with certainty say that this graph is there or not, because we don't know how to join them. So it is very important that we highlight the vertices in the boundary. And this is a rough idea how you would do deciding whether something occurs as a subgraph. But we wanted to work with logics, we wanted to evaluate formulas. So maybe first observation. So if you want to summarize this quickly, then you could say, if you know in F how all subgraphs of size Q intersect the boundary, and if you also know in H how all subgraphs of size Q intersect the boundary, then from this you can deduce how all subgraphs in F union H intersect the boundary. So this is kind of informally what I wanted to convince you about. And yeah, we wanted to evaluate logical formulas. So let's next turn to the next simple thing, which would be existential first order logic. You can only quantify existentially over vertices, and you can say whether they're adjacent or not. So here we can do the same thing. So existential first order logic is very, very similar to deciding whether a subgraph occurs or not. And we can again store how formulas of length at most Q intersect the boundary. So, but this is very informal right now, so we don't really know what it means for a formula to intersect the boundary. So what I mean by that is that the formula can talk about the vertices that are in the boundary and talk about them specifically. So we can have a formula like this. There exists a vertex A, and A should be adjacent to V1, and it should be adjacent to V2. So this stores the same kind of information that we did before with the subgraph counting. It basically stores that there is this path of length 2 from V1 to V2. So we're going to store these first order formulas. We don't need to store all of them, just the short ones. And we can specifically talk about the vertices in the boundary. And then hopefully you can kind of see that if we store how formulas of length Q intersect the boundary in F and in H, then we can deduce how they intersect the boundary in F union H. Okay, so this is the intuitive idea. Any questions about this? Otherwise, we will formalize it on the next slide. So now we come to perhaps a bit of a difficult definition. So I want to make sure that you all grasp this. We want to formalize this concept of storing how a formula intersects the boundary. So let's say we have a graph H, and the boundary are again the vertices V1 to Vk. What I want to define is a so-called Q type of the graph together with the boundary. So the Q type will be a set of MSO1 formulas, and these formulas, they have free variables, and for every vertex in the boundary, there will be one free variable. So if the boundary is V1 to Vk, then we have MSO1 formulas with free variables x1 to xk. And we put this formula into the Q type if and only if the formula is true after we plug in the vertices from the boundary. So if our formula C is true, if you evaluate it on the boundary, like plugging in V1 to Vk, then we put it into the Q type. And otherwise, we put it out of the Q type. So by looking at the Q type, we can get all the formulas that are true when evaluated on the boundary. And the second important thing is here this quantifier rank. So I'm not sure if we defined the concept of quantifier rank. The quantifier rank is how deeply nested quantifiers can be. So if you have a formula syst x1 for all x2 exists x3, this one would have quantifier rank 3 because you have 3 nested kinds of quantifiers. Or also if this was a universal for quantifier, still quantifier rank 3. On the other hand, if you had a formula like this, then this one will still have quantifier rank only 1 because the quantifiers are not nested here. Yep, question there.
Is this about alternating quantifiers or?
It is not about alternating
Oh.
quantifiers. Yes, exactly. Only how many quantifiers are nested within each other. So here, because it's not nested, this formula still has quantifier rank at most 1. So, and yeah, the Q of the Q type is the bound on the quantifier rank of the formulas that we want to store. Since we only want to evaluate some formula whose quantifier rank is bounded, we can take the quantifier rank of the thing that we want to evaluate in the end and only going to store Q types up until this quantifier rank. So, yeah.
And this quantifier rank is kind of like this is related to what you had on the previous slide of the length until we return to the boundary, right? Because that was how many things that we quantified over.
Yes. So if you have quantifier rank at most Q, you can say, for example, that there's a path of length Q that connects to something.
But now more general than just expressing that.
Yes. So this is quite a bit more general. So if you want, you can think of this Q type of saying, what can MSO1 say about the vertices in the boundary using at most Q quantifier nestings? So everything that can be expressed about the vertices inside the boundary using a bounded number of quantifiers or nested quantifiers, that is what we call the Q type. So in particular, there could be a formula that expresses there exists a coloring of the graph such that V1 to Vk are colored red. So if you remember for our coloring problem, we wanted to store our dynamic programming tables, whether a certain coloring of the boundary could be extended to the remaining graph or not. This kind of information is in particular also captured by the Q type. You could have a formula, the formula says V1 should have this color, V2 should have this color, V3 should have that color, and there exists a coloring of the remaining graph that is compatible with the coloring that you choose for the boundary vertices. Yeah.
Does the Q-type contain formulas that now talk specifically about V1? Because you mentioned that there are 3 variables and we can plug them in. And if I interpret that, I would think about, you can say there are 3 that are colored red, but you couldn't say there are V1, V2, and V5 colored red.
Yeah, that's a very good distinction. That has been confusing me also. First time I considered this. Yes, you can specifically talk about the vertices in the boundary, but the formula, like a formula works on variables. It does not work on vertices of the graph. So in the formula, you only mention the variables x1 to xk. But when you evaluate this formula, you plug in the vertices of the boundary. V1 gets mapped to x1, vk gets mapped to xk. So for evaluating purposes, these 3 variables are replaced by exactly the vertices in the boundary. So whenever you want to say V1 has some property, you say x1 has this property, and then it gets mapped when you evaluate this formula. Okay, so this Q-type is very, very big, contains a lot of information, in particular all these things about the 3 coloring types that we defined for dynamic programming. And now, if this type definition is clear, I would like to introduce to you this black box theorem that we're going to use to prove this. So the setting is the following. We have 2 graphs, F and H, and they intersect exactly in this boundary V1 to Vk. So far the same setting that is drawn here on the picture. And now the Pfefferman-Watt theorem states the following. If we know the Q-type of our boundary on F, and if we also know the Q-type in H, then from this information alone, we can deduce the Q-type in the union of the 2 graphs. The Q-type of F union H on the same boundary. So this sounds a bit strange, but yeah, you don't even need to look at the graph F or H itself. The only thing you really need is to look at the Q-type. And if you know those two Q-types, this contains all the information that you need to know to combine the types and get the type of the union of the 2 graphs. The form in which I just stated it now, with the intersection and that the graphs are not disjoint, this is actually not the original version in which this was published. So this is like some variant of Pfefferman-Watt theorem adapted to tree width. The usual classical version is a little bit simpler, so I would like to present that to you as well. So here again we have Q-types, but these Q-types, they don't talk about the vertices in the boundary. So we just have a Q-type of a graph H, and this is going to be all MSO sentences with no free variables of quantifier rank at most Q that are true on the graph. So no intersection and no free variables in the formulas. So this concept of a Q-type is a bit simpler, I suppose. And then the classical variant of Pfefferman-Watt theorem states that you can combine disjoint subgraphs. So you have now 2 graphs, F and H, whose intersection is empty. So they don't intersect anywhere. And if you combine them, then it's just a plain stupid disjoint union of 2 graphs. And then the Q-type of the disjoint union is completely, not complexity, is completely determined and can be computed from the Q-types of both subgraphs, the Q-type on F and the Q-type on G. And maybe I would like to sketch how you can get this advanced tree width version from the disjoint union version. So let's say we are in this setting. we have this boundary v1 to vk, and we want to compute, we have the Q type in F, the Q type in H, and we want to combine the Q type of both of them. What we can do is we want to use this version for disjoint subgraphs. And so, but this version of with the disjoint subgraphs, it does not talk about any specific vertices inside the boundary. But we can nevertheless highlight these vertices inside the boundary. We can just give every vertex inside the boundary a distinct color. So the vertex vi gets the color si, and the vertex vi is the only vertex with this color. Then, where before you would talk about some vertex should be equal to vi, you can instead ask, is the vertex colored with color si? So before you could ask y equal to xi, where xi corresponds to v, the vertex, the ith vertex in the boundary. Now you could ask si of y. So it contains this colorful graph. It contains the same kind of information without explicitly highlighting without explicitly mentioning the vertices in the boundary. And if you know the Q type on F, you can from this deduce the Q type of F prime. Because let's take some formula from here. This formula, for example, contains an atom of the form y(s)(1). So it contains an atom which says y should have color S1. But then this is the same as saying that y should be equal to x1, because only the vertex v1 has this color S1. And this is something, y equal to x1, that is in the Q type of F. So you can then, after you did this modification of the formula, check in the Q type of F whether the formula is there. And this is satisfied if and only if it is satisfied in F prime. So using some replacement tricks to get the Q type of these modified graphs, F prime and H prime. And now the classical Pfefferman-Watt theorem gives you also the Q type of the union of the two graphs. And the last step would be then from the Q type of the union to merge them together and get the Q type also from this overlapped version of it. So this is something that is maybe a bit more tricky, so I won't go too much into detail, but this is also possible. So in particular, if you would ask whether two vertices are adjacent in this graph, then you can, but you can only query the type here. You would have to ask, are they adjacent or do they have the same special color? If they have the same special color, then it is a vertex that should have been merged together and you would consider them the same. Yeah, sorry if this is a bit fuzzy. The proof is a bit more detailed. I can't go too much into the details. But yeah, this special version of Pfefferman-Watt, it follows from the disjoint version.
Can we maybe do like a quick example for if we have the formula, there's two red vertices, then it would be like wrong on F and H, but it would be right on the union of F and H, right?
Yeah, there's two red vertices. It would be wrong on, yeah, continue.
It would be wrong on F and it would be also wrong on H. It would then be right if we put F and H next to each other, like red is one color of the boundary. So then it would be correct. But then if we merge again, then it would be false again, right? Because then we merge the two red vertices into one. Like that's something we have to look out after, right?
Yeah, this is something we have to look out for, yeah. So how do we deal with this? So whenever we would quantify over a single vertex in F and H, we would, I guess, secretly quantify over 2 vertices and pick both copies of these vertices in F prime and H prime. So we could say that the vertices either talk about the same vertex or they are the 2 different copies in the graph. And then you would have to quantified over 4 vertices, this modified formula. So this slightly increases the quantifier alternation. So if you really want to do this, you would not highlight the vertices using colors, but you would highlight them as constant symbols that you can directly access, like a function with 0 input variables. You can just specifically talk about this vertex, that vertex, that vertex. They're part of the alphabet. So this is how you should, I think you're supposed to do it. This thing with the colors is not the right formalism, actually.
Yes, thank you.
So if we've been getting a bit warmed up with these Q types, then let's see how much time we have. We have like 15 minutes. So we can maybe talk a little bit already about how the proof is going to proceed. So we want to again do dynamic programming. And where before we would store our dynamic programming tables, and they were specifically to the problem. Now we want to store some very big dynamic programming tables, which are going to exactly store the Q types. So if we have some bag I, and this bag has a boundary V1 to VK, then we gonna store for every formula of quantifier rank at most Q, whether it is in the Q type or not in the Q type. And we, of course, we evaluate it on the subgraph. So for a bag VI, we are denoted by for a bag I, we denoted by VI all the vertices that are below the bag in the graph. And we're going to store for each formula with quantifier rank at most Q, we're going to store a 1 if it is true on G induced on VI, and we're going to store a 0 if it is not true. So if we can, and we store it in this function mi of xi. So if we can look into this mi, if the formula gets mapped to 1, it is in the Q type. If it's get mapped to 0, it is not in the Q type. So this is a lot of information that we're going to store. And I hope you can see already how we're going to combine this information during the dynamic programming stages by just applying Pfefferman-Wort. If you have the Q type here, you have the Q type here, you can merge it using Pfefferman-Wort. So the join operation of our dynamic programming tables will actually just be an application of Pfefferman-Wort. And then after we're done, we look again in the root. And let's say we want to know whether some formula phi is true, and this formula phi has quantifier rank at most Q, then we can check equally whether it's true on G induced to VR. So the root node, there the subgraph is the whole graph. And so we can simply look in the dynamic programming table of the root node whether phi gets mapped to 1. So the root node is, if we have a nice tree decomposition, then the bag contains no vertices. So all the formulas xi are actually sentences because they also contain no variables. So we can just check whether the formula evaluates to 1 by checking the entry. But we have to be careful because only our dynamic programming is only fast if our dynamic programming entries, tables are small. So we have a problem if we store huge tables, and on the first glance, it's maybe not immediately clear that these Q types are in fact small. So what we have to show is that the number of formulas with quantifier rank at most Q and at most tree width plus 1 variables, because this is the kind of thing that we store for every element in the bag, for every for every element in the bag, there will be one free variable, and the number of free variables, therefore at most true width plus 1. So the number of these formulas with few variables and few small quantifier rank, it should be bounded by some function of the tree width of G and our formula phi. Oh, my pen is now empty, so I have to draw by hand. Okay, so, and if we have bounded this number of functions, then we also bounded the number of dynamic programming entries, and that's good. But in principle, there can be a lot of such functions. And what happens, for example, if every vertex has a unique color? So we have n different colors, and then there could be a formula that says the vertex has color 1, the vertex has color 2, the vertex has color 3, up until the vertex has color n. So this would be n different formulas, and it would be way too much. So the number of formulas that we store needs to be independent of n. That's why we're going to do a first simple reduction rule. We're going to remove all colors of the graph that are not mentioned in our formula. So the formula that we're going to evaluate, it has length at most phi. So the number of formulas, the number of colors it can mention is only bounded by its length. And all colors that are not mentioned by the formula, we don't care about them. We can just remove them. And now the number of colors in the graph is bounded by phi. But there's a second simplification that we need to do. Like, formulas can be very, very long. It could be that we have a formula that exists in X, such as X is adjacent to X, and X is adjacent to X, and X is adjacent to X. So this formula is highly redundant, and we don't need to store this extra string. So we somehow have to boil them down into some kind of normal form whose length is bounded. So in this example, it would remove all these redundant entries. And so the claim that we want to show by induction is that, we're going to do induction by Q and show that there's only few formulas inside the type. And the base case is the following. We start with 0 quantifier rank, so quantifier-free formulas. And we want to show that the number of quantifier-free formulas, which at most k variables, is bounded by 2 to the 2 to the O of k times phi. So this is a doubly exponential function. So it's quite big, but it's a function of number of free variables and the formula length only. And so how does this proof proceed? So we can assume that the formula is in some kind of CNF normal form. So we have a bunch of clauses containing atoms like A or B, and maybe some other clause, C or D, something like that. And these atoms, A, B, C, D, they are of the form either two vertices are adjacent or non-adjacent, or it checks the colors of the vertices. So we have only k variables and only phi many colors. So the different number of atoms that this CNF formula can have are at most k times phi, and there are negations, maybe 2 times this much are there. So there's only this many number of atoms, and next we can assume that every clause contains every atom at most 1. So if there's 2 times the same atom, like x is equal to x and x is equal to x, we can drop one of them. So this way the length of each clause is bounded by 2 to this thing. No, the length of the clause is bounded by the number of possible atoms it can contain. And then the number of possible clauses you can have are 2 to the number of possible atoms, because you can, for every subset of atoms, you can have 1 clause. And then our formula, it is a conjunction of clauses. So you can have multiple sets of clauses. And how many clauses can there I guess you get another exponent. I can't write it like this. So this has bounded the number of clauses that you have to k times 2 raised by 2 times k times phi. And the number of formulas is then every possible subset of the clauses. So you raise it by another exponent, and this then bounds the number of possible formulas of this type, if you assume that they're in conjunctive normal form. So I feel like we're running out of time a little bit. So in the next lecture, we will complete this proof. Are there any questions up until now?
These SNK variables is refers to the free variables?
Yes, this k refers to the free variables that we have. Yeah.
The quantifiers themselves can introduce more variables.
Yes, exactly. So every quantifier that you introduce, it can capture one free variable. So for the next case, you have to, yeah, we're going to take that into account. And then in the next lecture, we will prove that in total, the number of formulas are roughly 2 to the 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 2 raised by tree width times phi. And the height of this tower is going to be something like twice the quantifier depth. So this is a lot of types. And actually, this cannot be much improved. So really, there are just this many types. And this is where the huge constants in the running time of Courcelle theorem comes from, by storing these very, very many types. Are there any questions? Otherwise, I think we've reached the end of this lecture today.
So another small one.
Yeah.
At this stage, at the root of this so-called decomposition, we don't just have the information of whether like the one formula that we were seeking and evaluate is that true or false, but we have like every single formula that holds for this graph.
So
a set of all these formulas.
yes, so in the end, in the root, we not only have the information whether one formula is true, but actually all formulas up to some fixed quantifier rank.
Yes.
So we're doing way, way more work than we need to, in a sense, but also we kind of have to do all this work because these formulas, they can influence each other and you really need to store all of them for the Pfefferman-Watt theorem. Any other questions? If not, then thanks for joining, and we'll see each other on Friday for the exercise for those of you who want to join, and for those who just do the lecture with each other in 1 week again. Thanks. Bye.